Hello everybody and welcome to my talk. Today we are going to discuss about two compilers, one which is kindly state-of-the-art, for example Graal, and the traditional C2. So welcome, my name is Ionut Balosin. Few words about me. I work as a software architect in Austria, in Vienna. We have a lot of projects on cloud, so a lot of challenges, and of course performance is one of the main constraints in some of the projects. Also, I'm a technical trainer, conduct courses in the software performance tuning and on software architecture topics. I write for my blog and especially for the InfoQ, and I attend conferences. That's all. What's the agenda for today? I structured the talk as follows. We will mainly cover three main points: Scalar replacement, virtual calls, vectorization, and loop optimizations. And at the end of the talk, I'll give you a summary or some advice in which context, particular to your application, you can use one compiler versus the other. Few things about the background of this talk. In April, I released a benchmark. I ran it against Java 12 at that time, where based on different optimization patterns, I actually compared these two compilers. However, now I have all the results for Java 13, but I have not published them yet. So if you like the talk and if you are keen in this area, please follow my website because soon I'll publish the new report. Few things about configuration, because today I will be sharing with you some benchmarks written in JMH. So the hardware configuration is CPU memory. I used Ubuntu as an operating system, Java, the last version. And what is important, actually, the version of the GMH and the number of warm-up iterations and real measurements iterations. Usually, if you measure only C2 performance, you don't need such longer warm-up. However, Graal, being written in Java, it usually needs that. In some cases, I found out even insufficient for Graal, so you basically need not 50, but probably 100 seconds until it reaches the steady state. This is a big notice. This talk is not about Enterprise Edition, Graal-E Enterprise Edition. And all the optimizations that I'm presenting today might differ in the Enterprise Edition. Enterprise Edition is a commercial product. However, all the talk is based on the open source OpenJDK. So I'm talking about just-in-time compiler in OpenJDK, not in Graal-E VM. And if you might wonder, why such comparison? Is it really a fair comparison? Well, I would say it depends, right? It depends on the viewpoint or from the perspective. If you are really a performance engineer, or if from the application standpoint, yes, it matters because at the end you are keen for struggling for more performance. Also, the licensing cost is important, so probably you want to keep in your project the cost lower. However, from the compiler perspective, those two are very different. And what is this difference? First of all, Graal has a Java-based implementation. I would say it's still early stage. This year it became production ready. However, it's still in the beginning. It's a nice, wonderful compiler, but still in the beginning. It targets a lot of languages, for example, JVM-based languages, dynamic languages, and native languages. So it has the notion of polyglot JVM. Using the JVM CI, starting Java actually 9, you can plug it in the OpenJDK and you can enable it. Implicitly, it's not enabled. And it also comes with AOT flavor, which is out of the scope for today's presentation. In comparison, C2 is the traditional. All of our code, or the majority of our code in production, still runs against C2. It's C++. It's very mature and was written to mainly optimize Java code. For example, in cases of functional style programming, it doesn't fit so well, but I will tell you later a bit more about this. And nowadays, the reality is that it reached a local maximum of performance, and probably its end of the design lifetime. Also, Cliff Click said that since he left actually Sun, it didn't suffer major changes, so not a lot of changes. During the latest releases, all the improvements were mainly focused on the vectorization and extending the intrinsic support. So this is about the context, this is the comparison between these two. However, nevertheless, the baseline for Graal, it's still C2. So it needs to be as good as C2, especially on production, on real applications, right? Because benchmarks are nice, but what matters is the production code. If you are really keen on understanding more things about Graal, I think it's really an innovative compiler. These are the three main papers I can recommend for you. First, it's about partial escape analysis. Then it's improved inlining. Then the third one is about guarding optimizations for efficient handling of speculative code. And where do you find this? These are the main publications, actually. The first one is called Partial Escape Analysis. In a nutshell, what it does, it actually analyzes the escapability of an object, and if that object escapes on the called branches, so the branches which are never taken, it avoids allocation. And this works, for example, on the IR, on the intermediate representation, not on the bytecode. Just to understand a bit more, I took an example from the paper itself. So this example, you find it in the paper. You have a key class, a very basic class. It has an index and a reference. It has the constructor, and it has also the synchronized equals. So it's a very, very trivial class. And you have the get value method, which is actually highlighted. Inside the get value, what you have to do, first you allocate an object, right? And then you ask if that object is equals with some predefined or some cached key, right? You return a cached value. So basically, if it follows on the true branch, you allocate something, but the allocation is actually useless because you always return a cached value. But if it falls on the other branch, right? So actually you store a reference, a strong reference to the previous key which was allocated, the previous key instance which was allocated initially. How Graal does, so this was the initial shape of the code, right? So how Graal does after optimizations like inlining and partial escape analysis, what's important to spot on this is it actually moves the allocation of the key from the bottom of the method inside the branch where it escapes. So, for example, in here, and in this case, actually, if you follow the first branch where after the equals method got inlined, it's never allocated. And this is called partial escape analysis. It actually moves the allocations to the branches it escapes. So in essence, if that branch is a cold branch, it's not taken during the runtime, the allocation doesn't happen. So this is one of the things. The second one is about improved inlining, and this is also a novel technique in comparison with C2, which actually decides inlining basically on the bytecode parsing, and the heuristics are I would say, are decided ahead of time. For example, it basically inlines based on the bytecode size of the method, and if the call depth of the method it's not bigger than 9. So if you have 9 methods in the chain, the 10th one it's not getting inline. And this it's actually doesn't fit well the modern programs, especially if you go and write functional code. And this techniques actually presents it's a new one, and actually what it does, it doesn't inline one by one method, it inlines clusters of methods and establishes during the runtime an adaptive threshold. So even if it actually reach the target of inlining, if it is still beneficial to inline, the inlining is triggered. So in a nutshell, these are the things: call side clustering, adaptive decision threshold, and deep inlining trials, which basically says it also assesses the efficiency of the inlining after the inlining happens. Another example from the paper, it's based on the Scalar code. You have a main method, which inside the body, there is an async, which calls a log. The log itself logs the get stack trace. And you have also the log for the arguments. And the log it's implemented, it's defined below. It calls actually, it dispatches to a for each. For each, which is actually defined in the Scala standard library. The thing is, the for each it's not inlined. It is inlined together with the get and the length. So the inliner decides during the runtime if it is beneficial to inline the for each only after it explores the get and the length. So they can be inlined together as a cluster. And here is the call tree representation. You have all the nodes. The nodes represent the call side. For example, you have the main method, and the main method calls async. You have in the middle, you have $anon. That one, it's because we are using a lambda in the example, and it corresponds to the constructor, which actually is the constructor of the VM anonymous class. Every time you create or declare a lambda, it's actually a VM anonymous class generated, and that one belongs to the constructor, which initializes that class. And the third one, it's actually the log. So basically, the main calls three methods: async, anon, and log. And you have also the legend. E stands for expanded, so the node was expanded. C stands for the node was not yet expanded. So in the initial phase, only the main is expanded, all the children are not expanding. Then during the expansion, actually you go through each child actually and decides, for example, in case of async, if it is beneficial to inline async or not. In this particular case, the inliner says, no, I don't inline async because I don't know much about this. I don't have enough information. You actually it goes next to the anon and then to log, and log it's expanded and it reaches the for each, the child method. And what's the new about this technique is because when it triggers the inlining, the for each, the child, it's not inline in that moment because it delays the inlining later on while it has more context and it explores more the call tree. So this is what I was told initially, because this heuristics decides at runtime if it is beneficial or to inline or not. So in some cases, because the inlining is really a difficult problem, so it delays until it gets more context. And the third paper, which actually I will just mention it, it's about speculative optimizations. It's very useful in case of dynamic languages. In a nutshell, what it does, every time it triggers an optimization, it's actually measured the cost of the optimization. Because when it gets and de-optimize things, you need to jump into the interpreter and you need to recreate the stack frame. In essence, the local variable array, the operand stack. So this is costly. So basically, it measures the cost of the optimization when it tries to optimize. Okay, so these were the three main papers. I recommend you to go through them if you want to understand more about Graal just-in-time compiler. Now let's back to the content of the presentation. So I will start with scalar replacement. Before going into scalar replacement, I'll just mention escape analysis. What is escape analysis? It's actually an analysis phase of the optimizer. So basically, each object, it's analyzed. So based on the scope it has, for example, it could have no escape scope. In this case, the objects, it's actually allocated locally. So there is only one thread which accesses that object. It can also have, for example, argument escape if you, for example, allocate it locally but pass it through a method as an argument. And also, it can have, for example, global escape if it is seen by multiple threads. And the thing is, based on the scope, the compiler can reduce the allocations for those objects that have no escape. because they are locally declared, so they don't escape, so they can reduce this allocation, and the technique is called scalar replacement. And this was a bit of the context just to prepare the stage, because now I'm going to present you 4 cases. The first case, it's about no escape. It's, the second one is I'm using an object with an array. This is the difference between the two. The third one is actually I'm using an object which always escapes on the call branch. And the fourth one, I'm creating an object, and that object escapes as it's passed as an argument. Okay, so let's start with the first case. In the first case, these, by the way, are JMage annotations. So the method noEscape, what it has, it declares a light object. You have the declaration of it below. It has 2 fields, F1 and F2. It creates an instance and actually returns the value of those fields, right? So in essence, it's very stupid because it's equivalent to F1 plus F2, right? The second case is I'm going to extend a bit. In this case, I'm going to create an object which is a bit heavier. Why it's heavier? Because I explicitly declare an array inside it. In this particular case, it's a byte array, which has, remember this, 128 size. I explicitly chose 128. And this is equivalent to F1 plus F2 plus length, because the object has no escape, right? So it doesn't make sense to allocate it anymore. The third case is I create an object locally, and based on the condition which is not known at runtime, that's the trick, it's not known, it's always evaluated during the, it's not known at compile time, it's always evaluated at runtime, but it's that branch, it's never taken, so in essence, the local object never escapes. And it always returns a cached value. So in this case, the partial escape analysis helps a lot, because based on the theory before, it moves the allocation inside the branch where it escapes. So basically, if that branch is never taken, the allocation doesn't trigger. And the last case, it's actually where I've created 2 objects with 2 arrays, and then I say if wrapper1, if those are equal, return true, otherwise return false. And the thing is, if wrapper1 has always no escape, because it never escapes, right? But wrapper2, it mainly depends during the runtime. If the equals method gets inlined, the wrapper2 has no escape. However, if it doesn't get inline due to whatever reason, for example, you explicitly disable the inlining for that method, it has argument escape. So these were the 4 cases. Now, I ran all of them based on the setup I told you before, and these are the charts. In essence, shorter bars means faster, because it's about the response time. And you, dark blue lines, you have the legend of the button corresponds to the C2, light blue corresponds to Graal. But to make it simpler for you, I highlighted where is the performance difference. So in a nutshell, C2 actually was able to be the same performance, the same parity with Graal only for the first case, for the no escape. In all the other cases, it couldn't reduce the number of allocations. Which leads to these conclusions. So if these conditions are not very clear based on the compilation, based on the bytecode analysis, right? So and if the object it's not clear that it escapes or not, C2 struggles to avoid those. And now getting back to the heavy object, I explicitly chose, for example, 128 size, because, for example, C2 by default doesn't consider escape arrays if the size is bigger than 64. So if you have such kind of objects, if you know in advance what would be an average size, and even if they have if they have local scope, they get allocated if the array is bigger than 64. So this was the first bunch of cases. The second is about the virtual calls. Again, just to prepare a bit the stage, just a few theory, because I will use these terms when I do the benchmarks. What's a monomorphic call side? You have a base class and you have a child class, right? So during the runtime, the compiler sees only one possible target implementation, and this is called the monomorphic call side. Then if it discovers a second possible target implementation, it's called bimorphic call side. The third case, starting with the third case, it's called megamorphic call side. So this is just terminology in a nutshell. And why I was referring to this, because I will use this in the benchmarks, just to understand better the test cases, right? And here I have a method which actually, it's called execute. It receives the C method, so basically it receives the parent. And what it does, it actually calls the compute. And compute during the runtime, it's a virtual call, because it could take, depending on the target implementation, it could take L1, L2, L3, and so on. What is very important, if you play with such scenarios, is to exclude the inliner for this situation. And that's why I explicitly say I don't want to inline, because if you don't inline and it gets inlined in the caller, you might not, for example, carefully measure the vtable lookup, the call itself. And here are all my test cases. So first, the monomorphic benchmark, it's actually very simple. It calls executed to only one possible target implementation. Second one calls the same method, which I explicitly say I don't want to be in line with two possible target implementations. And the third one calls with three possible target implementations, and so on. Fourth, fifth, and sixth are exactly the same. I tested all of this, and voila, these are the results. It's a lot of, they don't differ too much in a sense. They are around 3-ish nanoseconds, 4 nanoseconds. So me, honestly, I cannot take any conclusions. And also my advice for you is to not be biased to the results itself, but to understand the patterns and what happens behind. Because timings might slightly vary if you run from one hardware machine to another hardware machine, depends on the noise and so on. And however, in the nutshell, the first two were better for C2, and starting with the third were more in favor of Graal. What happened actually under the hood, if you profile this and if you zoom inside the assembly, this is the only evidence of proof what really happens. So this is the assembly. However, I clean it a lot, because it's very difficult to present assembly, to put it on the slides, especially because we are not very familiar with this. However, just to make it easier to present, so what it does actually, this is the bimorphic case. So it checks, because the compiler sees two implementations, right? So the bimorphic case says, hey, if the instance is of type L1, it jumps, and the implementation is in line. If it sees that the L2, it jumps, and the implementation is also in line. And because it saw only two implementations, but of course you can load dynamically another one. It jumps actually, and it's called in C2 in HotSpot terminology uncommon trap actually, and it gets and de-optimizes and switches back to an interpreter. Because as I said, it could be also the third and fourth possible implementation. As opposite, this is the Graal assembly generated. It's exactly the same mechanism. So it checks if it is L1, target invocation, it checks for L2, then for another possible implementation, it goes into the deop routine. So in a nutshell, both compilers rely on the same, let's say, approach, inline caching, and add some deoptimization routine or uncommon trap to handle another unseen possible implementations. The megamorphic megamorphic 3, which means I have a base class with 3 possible implementations. C2 doesn't do anything, so basically it does the vtable lookup, so it's a virtual call during the runtime. However, Graal still continues on the same pattern because the methods are so small, all are inlined, and there are jumps between each, so it actually checks if this is of type ELG1, goes to and execute, if it is ELG2, goes down, and then if it is ELG3, and for a fourth possible implementation, it jumps here. Because it could be like, for example, the fourth one, but was never loaded. In a nutshell, this is what Graal does. So it's able to devirtualize also the target implementations for the megamorphic call sites. And C2 actually has a limitation. It's there since a while. I would say there is also a bug on that, or an enhancement maybe. And in a nutshell, it's because of the polluted profile context, which means actually to use a method in different contexts using independent operand types. And this is there. To be honest, I don't think it really a performance bottleneck in a real code, in the production code, even if you stick with the third possible target invocation. However, yeah, I think it's good if it devirtualizes also even beyond that. And the last case is megamorphic fall with 4 possible implementation, 5, 6 are basically on the same pattern. So Graal inlines everything and does the chumps, and yeah, C2 virtual calls. Vectorization and loop optimizations. This is the next on my presentation. So let's suppose you have 2 arrays. You want to multiply 2 arrays, and there are during the runtime they can be triggered in a Scalar version, which means actually one operand type, one instruction, one by one. And they could be also in a vectorized fashion, which is actually carries the same instruction, right, and multiple operands at once, in particular in this case 4. And this it's also possible, of course, with hardware support, in essence with SIMD instructions, single instruction, multiple data. And we also, they are using also some hardware extensions, in particular registers. And you can see here XMM and YMM registers. Of course, there are a lot of more, but these 2 I refer in the upcoming slides. So an XMM register, it's a register with, you can store in it 4 floats, and YMM, it's double the size of XMM. So there are actually, it's spread across 256 bits, and you can, it can fit 8 floats. But this is not enough. In order to have vectorization, you also, the loop needs to be vectorized, because the compiler analyzes the loop, and based on some criteria, it decides if the loop is vectorizable or not. So first of all, in order for the loop to be vectorizable, it needs to be countable. What is a countable loop? This is from Wikipedia, actually. A countable loop, it's a loop which has the limit invariant, loop invariant. You can see for in the top, the limit. So that one needs to be loop invariant, and the stride itself needs to be constant. So in this case, it also enables the unrolling. It needs to have single entry, single exit. The code needs to be straight. So which means if you have switches, the vectorization doesn't happen at all. And if you have multiple loops, only the innermost it's vectorizable. In terms of functions, intrinsics are allowed. So this was a bit of theory. Now let's zoom inside the first example, what it has actually, you multiply 2 arrays, and the JMH benchmarks looks like that. In particular, I took a bigger size for the array because I wanted to bypass the CPU caching effect. So I don't want all the elements to be stored in first level of cache. And how it works actually, it's the multiply to array elements method, where you can traverse all the elements and multiply them. Performance-wise, in a nutshell, Graal was 4 times slower, 4.2 times slower. And the question is why? It's actually the same code. If you run it in OpenJDK with C2 with the default and you switch to the experimental Graal, you will encounter a slowness around 4 times. And let's try to understand what happens under the hood. As I said, maybe the figures are not so important, but it's important to understand the patterns. This is actually an optimization pattern for the loops, which is the wishful, I would say, because this is how a loop is optimized in its best shape. So what it has, actually it starts with a pre-loop, which actually it peels one iteration or a few iterations outside of the main loop. It's very beneficial in case there are some checks, because you check those in the pre-loop, and then if you jump in the main loop, you already don't have to check them anymore. Also alignment, also pre-filling of the caches. Then you have the vectorized main loop, which is actually the big chunk of it, where in this case were used YMM registers. So in one YMM register, 256 bits, you can store 8 floats. So basically, because the loop is also unrolled with a factor of 4, you cover 32 actually multiplications per loop cycle. And then if there is a remaining of the elements which is less than 32 but bigger than 8, right? So it still continues with a vectorized post loop, and it does 8 at a time. And if it is still a remaining, one by one until it reaches the end of the elements. So this is actually the pattern in case of C2. Assembly-wise, this is the Scalar preloop. You can see in the bold the multiplication and also the incrementer of R13D. And the pattern in pseudocode at the bottom. Then it jumps inside the vectorized main loop, and inside the vectorized main loop, as I said, there are 4 multiplications. Each multiplication tackles 8 floats, so in essence 32 per cycle. And you have also the pattern at the bottom. And if there is a remaining, and that remaining, it's less than 32 but bigger than 8, it does still vectorize, but 8 by 8, and 1 by 1 until it reaches the end. So this is C2 case. The storing case of Graal, it's this one. So Graal does, of course, peeling, because peeling is one of the techniques very used. And the main difference is the main body of the loop, it's neither vectorized nor unrolled. So what it does, it actually multiplies 1 by 1 until it reaches the end. So this is the assembly for the loop peeling. You can see 2 additions up front, then it jumps to L001, and then inside this is the main body where it does multiplication and it increments the EDX of 1 by 1 until the end. So, which actually explains the difference in performance between these 2 cases, why Graal was so slow, the compiler was so slow, versus C2. Conclusions, these were already mentioned. So C2 uses YMM, AVX2 registers, main loop, post loop, the reminder, it's Scalar, 1 by 1. And Graal doesn't do such things. It's still Scalar 1 by 1. Vectorization is actually a big missing feature in OpenJDK. So it's not present at all in OpenJDK. If you have a lot of computation operations, a lot of loop, be aware, because Graal in OpenJDK currently has no support for that. And in particular, loop unrolling was not met in this context, but I would not say it's totally missing in OpenJDK. The next case is the same test, but inside using an int stride, I switch to a long stride. The code is the same. In this case, I just change, you can see it highlighted in pink, from int to long, just one modifier type. So from int to long, and in this case the performance was mainly or roughly the same. A degradation in case of C2 about 4.2x slower. Graal was around the same. But now the question is, what happens just by changing the stride from one type to another, so from int to long? In this case, what happens, this is the high-level picture. In both cases, both compiler uses the Scalar loop, neither vectorized nor unrolled, so it actually does Scalar one by one until it reaches the end. And it's not all, because it's also important, there is a save point pool injected. So in each loop cycle, it checks if it needs to reach the save point. Actually, a save point, it's a stop the work pause, and all the threads needs to be stopped. It's useful in case of, for example, garbage collector marking phase, the optimizations, code flashing, bias revocation. These optimizations, so in this case, it checks every time. So of course, it takes more time. And the same case for Graal actually. Graal inserts the same save point pool. That's why actually the performance is almost there, because the patterns also to optimize are very similar. In conclusion, one main Scalar loop, no loop unrolling, no vectorization, and the save point which was added. The last case in my talk is about the unpredictable branch. What it is about, actually I have an array, imagine, and I initialize that array with values, random values between 0 and a threshold. And because they are random values, they could be less than threshold value during the runtime, and there is a condition which actually checks if the value is half of the threshold, I sum it up. Otherwise, I don't sum it up. And this causes the unpredictability of the branch, because some of the values might be bigger, some of the values might not be bigger. So it's not a predictable pattern. I also created the baseline, because you need a reference to measure against. So the baseline, which doesn't have any branch at all, and another case, the middle case, where I have a branch, but that branch is very predictable. And the performance outlier, I would say, was still in case of Graal. So for the previous code, for this code, actually, if you run it with C2 and if you run it with Graal, it's 6-7 times slower. Why is that? Again, it's important to understand the reasons behind. So first, the same pattern, it peels the loop, few iterations. Then the difference is the Scalar main loop is unrolled with a factor of 8, so it does 8 by 8 sums. And if there is a remaining, it goes 1 by 1. Assembly-wise, this is the proof. Actually, you can see there are 8 additions. Actually, it's power of 2. 8 additions, and then there are some conditional move less. And at the end, it sums and gets to the next iteration. And the remaining, I didn't include it, but it's 1 by 1. Graal does actually the same loop peeling, and the difference is with the main loop, it goes 1 by 1, so still no loop unrolling. I would say it was the second case where it doesn't trigger the unrolling. Assembly, it's like this. So the main loop, it incremented 1 by 1. So basically, that's the difference in performance. Conclusions: C2 main loop unrolled with a factor of 8, and in case of Graal, it doesn't do loop unrolling. Surprisingly or not, this was the second, I would say, basic case where I couldn't find the unrolling in my test sample. And now let's move to some summary and takeaways based on what I have presented here, right? So all the techniques, Scalar replacement was actually better for Graal. Virtual calls are better optimized in Graal. Vectorization, this is definitely missing in Graal, OpenJDK. Loops, and also here I presented only a few cases, but I tested with more cases, and I think loop unrolling, it's really wonderful in C2. So in this case, C2 really wins. And I haven't mentioned intrinsics in this talk. However, Jean-Philippe Halemi worked for Intel. A few months ago, he had a presentation where also presented the state, and it might be outdated, but just a few months ago, the number of intrinsics were not so great in Graal. But these are actually very abstract, right? Because we are using real applications. We don't care in real applications about, I don't know, virtual calls, Scalar replacement. And this, I tried actually to come up with some guidelines for you in order to properly identify which is a potential compiler that you need to probably enable and test it in your application based on some criteria. So for example, if you create a lot of objects, Graal does a better job. If your application has a high degree of polymorphic calls, the same, Graal looks better. And if you have a myriad of tiny nested calls because of the improving lining in the Graal and the paper I mentioned, I think it definitely handles it in a better way. And this goes hand in hand with functional programming, which, for example, Scala plays better if you enable Graal. However, on the other side, if you have a lot of loops, a lot of mathematical operations, or if you want a quicker startup performance, what it means actually, quicker startup performance is due to the native implementation of the C2. You will find if you try with Graal, it needs way longer warm-up iteration than C2. Sometimes you really need to warm up a lot until it reaches the steady state, and also to profile to see that. And also the overhead. The overhead is, in my opinion, lower in C2. Again, it's a native compiler, and Graal written in Java needs to compile as well. If you are using some versions for OpenJDK, be careful, because in 8, it's not there. It's even JVM CI, it's not there, but to my knowledge, there are some backports. So if you really want to use Graal in 8, it might be possible. In 9, there is the JVM CI enabled, but you explicitly need to add the Graal just-in-time compiler, and starting with 10, you have both. However, as I mentioned, Graal is still experimental, so you need to explicit. In terms of GC compatibility, if you are using serial, I don't think somebody uses serial still. Maybe, but in very corner cases, both are compatible with serial. Parallel, it's actually the same collector, so both Graal and C2 are compatible. CMS, if you enable CMS in the same time Graal, the JVM doesn't start, and the message JVM CI compiler doesn't support. Anyway, CMS will be soon removed. It's deprecated currently, but in reality, a lot of people still are using for latency. Anyway, but it doesn't work with Graal. At the moment, G1, yes, works. ZGC, I would say it's quite interesting. I personally tested it because, as I mentioned initially, we are testing some of the things internally just to decide what to take. And it's a very promising collector. However, if you try to use it, it's still experimental. If you want to use it, both ZGC and Graal, the same case, JVM CI doesn't support it. Epsilon, you use Epsilon mainly for the benchmarks to have a baseline. It doesn't work with Graal, and Shenandoah, the same case. Shenandoah, if you want to enable it in the Oracle builds, you don't find it. However, in the Red Hat, you will find it there, so you can take it. But it doesn't work with Graal. That was all. As I mentioned, if you are interested in this, you can also help me to improve the set of benchmarks. You can get in touch with me. The code is not public. It was shared with some guys from different companies, but it's not publicly shared. So now I'll publish a new report, a very comprehensive, more comprehensive, not very comprehensive than the existing one. Yeah, the slides are anyway public. Thanks a lot for your attention. Now, if I have to answer the initial question, which one offers better runtime performance, I really don't know. You have to measure it by your own. It's always good to measure, but my advice is to really measure on a real code, on production, on code that you deploy in production. Not on the micro benchmarks are good, but especially if you are using GMH, GMH reaches the maximum performance. In most of the cases, you probably don't reach that performance in production. So enable it in production or on production code, profile it, and then decide by yourself what better fits your context. Thanks.